Right, I'll go over to, they're quite short examples. So they're from the book, your online textbook. So I won't write them out, but I'll read them as I go through. So we've basically got a smooth ball falling vertically at 5 meters per second. It strikes a smooth plane which is inclined at an angle of alpha to the horizontal, where tan alpha is a half, E is a half, and we want to find the speed of the ball immediately after impact. So this is, I know it's sort of v velocity, but we also use v for speed, so I'm not writing that as a vector. We need to really think about resolving parallel and perpendicular to this slope, because we're assuming that there's no friction, and so the impulse is working in that direction perpendicular to the slope still. So we can almost think about doing this. So you're splitting the velocity. I mean, use whatever notation you want. You could use V1, V2. I quite like doing V perpendicular, V parallel. So you can split it in components, parallel, perpendicular to that slope. So to find the velocity parallel to the slope, then the velocity parallel to the slope, or parallel to the plane, will be unchanged by that impact. We know that tan alpha is equal to a half, and if you come into your diagram, if I come across here with a horizontal, that angle sitting in there is equal to alpha. And then if I come down here, so we're going parallel, perpendicular to the slope with this velocity coming down here, we can split it. This is alpha, so this is 90. Here, this one is 90 minus alpha, and so this angle up here is also equal to alpha. And so the velocity parallel to the slope is unchanged, and that's equal to 5 sine alpha. And then we know tan alpha is a half. You can do a triangle on that, just to keep exact form. And so sine alpha is 1 over the square root of 5. So this one here is equal to, let's make that clear, 5 over root 5, which is equal to root 5. And then perpendicular to the slope, so the velocity perpendicular to the slope is going to be equal to the coefficient of restitution. So you're going to expect to lose some velocity perpendicular to the slope. So it's E times 5 cos alpha. So that's 5 cos alpha. Remember, we're dealing with speeds and effect, and then we combine them together to give a velocity. But this question is more working with speeds. So this is 1/3. No, sorry, E is a half. So 1/2 times 5 times cos alpha, which will be 2 over root 5 from here. And working that lot through, that is also equal to root 5. They won't always come out the same, obviously. And so the speed after impact is equal to the square root of root 5 squared plus root 5 squared, which is root 10 meters per second. So that's that one. I'm hoping to get this on one. I think I'll be able to. Example 3 from page 98 in your books, I believe. I think you did one of these last lesson potentially, but I just thought I'd go over one as well. So for this one, we've got a smooth vertical ball, mass 2 kilograms, everything's in SI units, which it needs to be. It's moving in the XY plane. So this is X, this is Y, and it hits a fixed smooth vertical wall which contains the Y axis. So the wall is coming up like this from the XY plane. The velocity of the ball just before impact is -6, -4. So do look at that to work out the direction. So I'm taking my positive X that way, positive Y that way. And so it'll be coming down like so. So back 6, down 4. And then the coefficient of restitution is 1/3. And we want to find the velocity immediately after the impact. So we're trying to find velocity after, which is PQ. You might want to, I don't know, I don't know. I seem to be liking my notation very much for some of this, but velocity after you could call V if you wanted to. And actually for this one, you can pretty much write it down because the stuff parallel to plane of impact, so the line of impact, is going to remain unchanged. So it's still going to be going -4 parallel. And then E is 1/3, so the speed is going to be 6 times 1/3, which is 2, and the direction has changed. So the velocity after impact is 2 - 4. So having it in this form, actually, it's, all that resolving is just done for you for this question. We do need to move on to these being at an angle, and we'll talk about that later. But it's good to do a couple where they're not first, I think. And then part B, you wanted the kinetic energy lost in the collision. And so that's just 1/2 m v squared, which will be 6 squared plus 4 squared. So that's your initial kinetic energy minus 1/2 m 2 squared plus 4 squared final kinetic energy. You could obviously combine these in if you want to. I just quite like keeping them separate for some reason, but you're very welcome to combine them together. And that gives you 32 joules. And then part C is the angle of deflection of the ball, which, if you remember, is alpha plus beta, where alpha is this one and beta is this one. And so that's just a little bit of trig. So tan alpha is equal to opposite over adjacent, so 6/4. And tan beta is opposite over adjacent, so it's 2/4, isn't it? Yeah, so that's 2, that's 4. And then if you just do arctan of those, you end up with alpha plus beta equals 82.9 degrees. So when they're in component form like that, it's actually quite nice, but they'll get a little bit harder when we need to put that line of contact at an angle as well. But yeah, we'll get there with those in probably next lesson.